I'm going to start talking about new stuff. So if you are like to follow along in your notebook and write your own notes, or if you like using OneNote to write your notes, or if you just like to sit and listen, you can just sit and listen. Again, everything that I do in class, one, we're recording, and I'm posting the videos to OneNote. You may have already seen them in chapter 1. The videos I put in there the other day. And 2, all of my notes are going into the content library. So the titles for all of my notes are just the date. So you would see, it should be easy to tell if you miss class, like what did I miss? Well, just find the stuff from the correct date. So that should be pretty easy, right? Okay. So yesterday, we had spent a bunch of time talking about sets, right? Today, we're going to start talking about another special kind of set. This kind of set is called a relation. Okay, so a relation is a set of ordered pairs where the x values all come from a set D and the y values all come from a set R. When we say ordered pairs, we're just talking about like an x comma y, like a coordinate. Now these sets D and R have a special name. So we call the set D the domain, and we call the set R the range. So just like yesterday, a relation is a type of set. So we talked yesterday about sets that could be finite and sets that could be infinite. We can have relations that are finite and relations that are infinite because they're just a kind of set. Okay? The only difference is, the only thing that's special about a relation is that a set can have anything in it. A relation specifically has only ordered pairs in it. Okay? But that's the idea. So just like a little example, since a relation is a set, we can name it with a capital letter. And we'll start with those squiggly brackets. And the only thing in the set is some ordered pairs. So this is an example of a relation. Right? It just contains these 4 ordered pairs. If I asked you what the domain was for this relation, the domain we said was where the x values come from. So if I look at the x values, we'd say the domain then is the set 1, 2, 3, 4. And we said that the range is the y values. So our range is the set 2, 3, 4, 5. Is that okay? So all we've done here is kind of just establish some vocabulary, right? And talk about like what these different parts of this relation are. So if I asked you a question here, maybe I ask you, is 1 a member of the set A? What would you say?
Yeah.
You should say no. Why would we? It is a member of D, correct. But the things in A are all ordered pairs, right? If I asked you, is 1, 2 in A, that we would answer yes to.
So set A is the relation?
So A is the relation. Yep, it's the set of ordered pairs. At least in this example. A is an arbitrary name, though. I just picked a letter. Is everybody okay with that? The difference between the things that are in the relation versus the things that would be in the domain or range, per se? Okay, so the relation is, the things in there are always ordered pairs and not individual numbers. So far, so good. So again, nothing tricky, no calculation involved, just some kind of definitions, right? A little bit of notation and how we represent things. In this class, we're going to talk about 4 different ways to represent a relation. So the first way is as a set of ordered pairs. Which would be just like we saw above, right? So when we talk about a set of ordered pairs, it's just a set of ordered pairs. Now that set of ordered pairs could be finite or infinite. For this kind of a class, we really would only be talking about finite ones. If you're in the honors class, we'll talk about, we would also expect that we're able to deal with infinite situations, but not here. Again, like between the two classes, we do basically the same stuff, but here we'll do a little bit less and go a little bit slower through the things that we do. But we're doing this, you know, if you looked at their lesson and our lesson, we did basically the same things yesterday because, you know, we're just introducing some ideas. But as we go, the classes will get more and more different. They'll both start at the same place and cover the same things. Just the depth kind of changes. The second way we can represent a relation is with something called a mapping diagram. So what a mapping diagram looks like is basically we have 2 ovals. One oval is going to represent the domain and one oval is going to represent the range. Then we'll write in the numbers that are in the domain and range in the appropriate oval. And then we'll just draw an arrow from one thing in the domain to one thing in the range, or from a thing in the domain to a thing in the range. Doesn't necessarily have to be one. And each of these arrows basically is representing an ordered pair. So for example, this arrow that I've highlighted in yellow represents the ordered pair 1, 5. This arrow that we've highlighted in blue would represent the ordered pair. I picked red there. 2, -2. And this ordered pair that we've highlighted in green would represent the ordered pair 3, 7. Is everybody okay with how the mapping diagram is really describing the same information as a set of ordered pairs? It's just doing it visually rather than symbolically, right? No big deal there. Everybody's cool? Okay. The next representation is as a graph. So if our relation is finite, that there's like 7 of them or 10 of them or 15 or 200, but there's like a fixed amount, it's not infinite. So if we have a finite relation, our graph would just look like some points, right? But there would be discrete points. So individual points just scattered around. However, if our relation is infinite, our graph is going to have like a curve or a line segment or something on it. Remember from your geometry class last year that even a line segment contains infinitely many points. So as long as you have some piece of the graph that's connected, you have an infinite relation going on there, even if there are other points scattered around. If you have one part of it that's connected, there's infinitely many points on a segment. So if you have any connection on there, you're dealing with an infinite relation. Okay with that? You remember that from geometry? I think that was an axiom and not like a theorem or anything else. Remember the difference between an axiom and a theorem? The axioms were things that you assume to be true without proof. Because how would you prove there's infinitely many points on a line? Like that's just one of those things you have to like take as a fundamental principle of geometry. Usually the axioms seem very obvious. And our last of the 4 representations is an equation. So when we talk about the equation, really we're talking about infinite relations only. Right? There's not really a way to write a finite relation with an equation. And similarly, I guess we probably should have noted back here when we did the mapping diagrams, this is really for finite relations. Right? Because I can't list out the entire domain and range and draw arrows if there's infinitely many of them, right? So an example would be something like y equals 3x plus 5. So your equation should have 2 variables in it. It should have an x and a y, typically. That equation that I wrote down would be one that you would recognize, hopefully, right? That's just the y equals mx plus b, your slope-intercept equation for a line. But that's an example of an equation that would represent a relation. Okay. Next up, we're going to talk about a very special kind of relation. So we say that a function is a relation where every item in the domain pairs with exactly one item in the range. So it's just a little aside to give you an idea of the hierarchy going on here. You know, you have your sets. A type of set would be a relation, but there's sets that are not relations. And then a special type of relation is the function. So you have a situation, like a nested situation like this. So all functions are sets. All functions are relations, but all relations are not functions, and all sets are not relations. Everybody okay with that? Does the visual kind of help with the hierarchy going on here? And we saw situations like this a lot last year in your geometry class, right? Like every square is a parallelogram, but every parallelogram is not a square. Right? When you talked about those quadrilaterals, do you guys still do the dichotomous key thing? So that's the same idea there, right? Okay, good. I was actually the one that wrote that assignment years and years ago for the dichotomous key. Yes? This is just an aside. Like, it's not necessarily specific to the definition. It's just a way to visualize these three, set, relation, and function, visually. It's not really any new information. It's just me kind of commenting on the relationship between those three things. Is that okay? Okay. So yeah, again, if you can't read anything or you're not sure what something means, please stop and ask. Perfectly fine to do that. It's important that you understand what's going on. I know that I have a hard time letting go and moving on and continuing to listen when I have a question about something like that. So if something's bothering you or you're not sure about, please stop me and ask. That's absolutely the right thing to do. Even if it's like just like something stupid like this where I just what I'm calling just like a comment or whatever. Perfectly fine. I'm not saying that your question was stupid, but it's like a stupid thing for me to have written there, right? Like, it doesn't really matter kind of thing. But you don't know that if you don't know what it meant or what it said, right? Like, you didn't know that it didn't matter. So, like, ask the question. It's good. Okay. I just want to be clear. I wasn't trying to say that it was a stupid question. Okay. There'll be plenty of time for stupid questions later, which I welcome, right? That wasn't one of them, though. Okay. What I'm going to do now is we're going to spend a bunch of time now doing a bunch of examples where we try to tell the difference between a function and try to tell if a relation is a function or not. Let me phrase it that way. Okay, so I'm going to write up a relation, and we're going to do relations in all of these different forms and try to talk about how we can tell if it's a function or not, and then we'll look at some specific examples while we're doing that. Sound good? So this is an important skill and something that would absolutely, you'll do in the homework and would be like a testable or quizzable skill, would be telling if something's a function or not. So these are good examples to kind of pay attention to and participate with and all that kind of jazz. And we'll do a bunch of them just so that we get, that you get a lot of opportunity to do that. So let's say we have this relation that's just a set of ordered pairs. The ordered pairs are 2, 3, 3, 5, -1, 0, and 0, 6. And what we're being asked to do in all of these examples is try to determine whether it's a function or not. Okay with that? So if we want to decide if something is a function, we really need to be familiar with the definition of a function. So let's scoot back up there and reread that definition here real quick, because we probably wrote it down and obviously didn't memorize it the first time we've heard it. So it says a function is a relation. What we drew was a relation, right? It was a set of ordered pairs, so we have that part of it, where every item in the domain pairs with exactly one item in the range. Okay? So I see that these ordered pairs, each x is paired with a y. So the x's all got used. They all have a partner. That's good. So we have the every item in the domain part covered. Now what we have to check is to make sure that those domains only go to one range. So basically what I'm going to do is I'm going to look at the x values and make sure that none of them repeat. Right? If I had a repeated x value, that would say like 1 would go to 7, and then 1 might also go to 9. We don't want that. That's not a function. Is everybody okay there? Since I see no repeated x values here, my conclusion is that this is a function. Yes.
Wait, so if it has one range, the range is like 2 or something, if it's to put all of them, then it won't be a function.
So let's look at that as an example, right? That's a perfectly reasonable question and a good thing to do as an example. So I've taken the same relation that we had before, but this time all the y coordinates are the same. Okay? This is what you're asking about, right? It's a good question. So if we're checking to see if it's a function, is it a relation at least? Yes, because it's a set of ordered pairs. Do all the x's have a partner?
Yeah.
Yes. Does any x have more than one partner? No, right? 2 has only one partner. 3 has only one partner. -1 has only one partner. 0 has only one partner. So this is a function. Even though the y values repeat, still a function. So what wouldn't be a function? What if we took the same thing, but this time all the x values were 2 instead of all the y values being 2? So here, it's a relation, right? All the x's have a partner, check. But if I look, I have x's that are used more than once, right? This is saying that we have this one x value, x equals 2, goes to 4 different y values. This is not a function. So when we're determining if something's a function or not, we really only care about the x's. The y's can be used as many times as they want. Doesn't affect us being a function. There's another property where the number of y values, or how many times y values are used matters, but not right here, not for a function. The x's cannot repeat. Correct. Yes.
Okay, this is showing sound stupid.
Nope, go ahead.
Is it still a function like if the first order pair was like 2, 2?
Okay.
Oh, yeah, it is. This is up there. Okay.
Right. Yep. So you asked about this one. So it can be, but it doesn't guarantee it will be, right?
Right.
So if this one, if I had changed this to be a 2 also, it's still not a function. So again, the x and y's being the same doesn't matter, right? You just need to make sure all your x coordinates are different, is what we're checking. Do we feel good about looking at a set of ordered pairs and determining if it's a function or not? Basically, excuse me, basically boils down to looking for repeated x's. Okay. let's do some with some mapping diagrams. Is this a function?
No.
No, why not?
It's the last line.
We have an item in the domain that's not paired with anything, right? So it doesn't matter that the 5 over here isn't paired with anything, only about the 3. In fact, if we deleted the 5, still not a function, right? But if we deleted the 3 and left the 5 there, that is still a function. So this is not a function. So we only care about what's going on in the domain. Is everybody okay with that idea? Is this a function? No, what's the problem?
3, 2.
Good. 3 is going to 2 different places. That domain is being used twice. This is not a function. Very good. Does everybody feel okay here? Do I need to slow down? If I get going too fast, holler at me. I know sometimes it takes a minute to draw out the mapping diagrams. I don't want to get anybody like in a tizzy on the second day of class about it. So for the third day, is this our third class? This year's almost over. Yeah. See? Almost over. The blink of an eye and it'll be over. Actually, let's do this. How about this one? Is this a function?
Yes.
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 So again, we're checking, are all the x's used? Yes. Are they all going to one place?
Oh, yeah.
Yes. Does it matter that 2 of them go to the same place?
No.
No. Again, the x is the only part we care about, not the y. So it's what's happening on the domain side or the x side that we worry about, not what's happening on the range side. Are we doing enough good of these examples, like weird stuff happening to where we're getting a good intuition about what's going on here? I tried to vary the examples enough so that they're, you can see what's going on, right? I feel like I'm pretty good at picking, like, well, what if this happens as my next example? Let's see, G next, right? That's my next letter in the alphabet. I think so. Okay. So what if we were looking at some graphs? This graph is just a bunch of points. In this situation where you're looking at graphs, really all we need to worry about is the repeated part. We can assume that everything's got a pair, or else you couldn't put a point there. What would it look like graphically, though, if 2 coordinates have the same x value? So you have, yes?
It'd be like one top.
Exactly. Excellent. So you'd have 1 on top of each other. So for example, if we had the point like 1, 2, and 1, 3, 1, 2 would be like here, and 1, 3 would be there, right? So the tool that we'll use for graphs is something called the vertical line test, that I abbreviate that as VLT. And this says, if you can draw a vertical line that intersects a graph more than once, that graph does not represent a function. So if we look at this set of points here that we plotted, can we draw such a vertical line? I tried to make it so it looked like you could. Right? Seems like these two are the problem. Since I can draw a vertical line that intersects those 2 points, we'll say that this is not a function. Now, this vertical line test is really the same thing as what we did before, right? We're just checking for repeated x-coordinates. This is just a visual way to do it, since a graph is really a visual representation. Is everybody okay with that? Ooh. Okay. Was it okay for me to scroll? I felt like I paused there for a minute. Are we cool? All right. Remember, graphs can be infinite or finite relations. What if we have an infinite relation that whose graph looks like this? Does this represent a function? Well, let's apply the vertical line test. Can we draw a vertical line that intersects this graph more than once? No, right? So no matter where we draw that vertical line at, all we're getting is a single point of intersection. So we'd say that this is a function. Everybody's okay there? Let's do another. How about this graph that kind of looks like a circle? Is this a function? No, why not? Yeah, almost any vertical line you draw is going to intersect the graph more than once, right? Does it matter that there are some vertical lines you draw that don't intersect the graph? Does it matter that there's some vertical lines that you can draw that intersect it only once? No. The fact that I can draw a vertical line, all you need is one. Here we have many. But if you can draw a single line that intersects the graph more than once, not a function. Let's see. So here our graph is J plus this little point. Right? So I drew this extra point in. I'll make it big so it's obvious that it's an extra point. Does this represent a function? Why not? Yeah, because of the point, right? So there, if I draw a vertical line that goes through that point, it's also going to intersect that line. Yep, that's why I made a big deal about it afterwards. It's easy to overlook it because it's like, oh, you just goobered on the paper there. It's like, no, that point's supposed to be there. That was important. Do we feel okay with this idea? Okay. So what I want to do now is I want to go back through these examples and talk about the domains and ranges for each of these. For some of them, we're not done yet. We didn't talk about any with equations, right? We got to do that part first. I'm sorry. Let's do some equation ones. My bad. I got excited and tried jumping ahead. We're not there yet. Okay. So one way you could do this kind of a problem is you could use some prior knowledge. If you look at this equation, does this look like a form that's familiar?
Yeah.
Yes. What do you recognize this as?
Y
Y equals
equals mx.
mx plus b. This is a slope-intercept equation. What is the shape of the graph for something that's y equals mx plus b? What do you get when you graph something like that? A diagonal line, right? So I know that the diagonal line slope is 3 and the y-intercept is -1. So it's going to look something like this. Does it matter that I have it precisely on the sheet of paper? Not for a line, right? I just have to know it's some kind of diagonal line. That's enough, right? It's not straight up and down. It's not straight side to side. It's something on a diagonal. It doesn't even matter if it's sloping up or sloping down, really, for this. So I'm just going to translate it into a graph. Does this pass a vertical line test? Yeah, right? Any vertical line I draw is going to intersect this just one time. You guys agree with that?
Yeah.
So we can conclude that this is a function. So that's good, right? We used some prior knowledge. We said, okay, I know what the graph of this is going to look like-ish. Again, didn't need to know precisely what it was going to look like. It just enough. And any non-vertical line is going to represent a function, right? So I can deal with that. JKL is next, I think. I draw my L's cursive because you can't tell the difference between a lowercase l and a 1 when I'm writing. And in math class, that's a problem. So I draw my L's cursive because of that. It's the same reason why, like, when I write my Z's, I'm going to put a bar through the middle, because you can't tell the difference between my Z and a 2 without the bar. So I try, over the years, I've come up with these, like, how do I need to modify this symbol so it's clear whether it's a, letter or number or whatever. All right, so let's look at this equation. You might recognize the form for this equation. If you did recognize it, you would have talked about it last year in your geometry class. I couldn't really hear. You're saying something though?
It starts, I forget what it's called. I don't know. Someone, I don't know.
Yes. So it is in some way related to the Pythagorean theorem, which is what you're I think the two of you guys are referencing. Yeah. It's actually the equation for a circle is of the form is of this form where h comma k is the center of the circle and r is its radius. Now it sounds like we didn't recognize that, which is okay. Again, I can't remember between honors geometry and regular geometry how far the two classes get. It's been a long time since I've taught one of those two. And it wouldn't surprise me that in the regular geometry class you didn't talk about circles or equations for circles. So what would we do if we didn't recognize the form of this as a specific shape for a graph? Okay, plot it. The problem is that it's not written as y equals something. So let's do that. So the first thing I'm going to do is I'll just subtract x squared from both sides so that I can get the y by itself. Everybody's okay with that idea? So I'm going to get the y by itself so it's in a form where it's going to be easy to kind of plot things or whatnot. Now I have to get that squared off of the y also, right? How do I get rid of that? So how do I get rid of the squared that's on the y? Dividing by 2 would get rid of a 2 that's a coefficient, because like division undoes multiplication, right? But it doesn't undo an exponent. What operation is going to undo an exponent? Okay, so exponents never distribute, so that's a right from the get-go. I'm going to say that. Square root. Yeah, exactly. Okay, so we'll square root both sides of this. Now, there's one important thing that we have to remember when we square root both sides of an equation. Does anybody remember that?
The plus or minus.
The plus or minus. Very good. Do you remember why we need that? Why we create a plus or minus when this happens? So like, let's say that we have x squared equals 4, right? What number squared gives me 4? 2. And also negative 2. That's why we need a plus or minus, because when we have the squared there, more often than not, that has 2 answers to it. Everybody's okay there? All right. So we've done that now. And now the suggestion was to plot this. Now that the y is by itself, it's in a form that's going to be easy to, generate some points for. So let's pick a value for x. I'm just going to pick 0 because it's an easy value to deal with. There's nothing magic about this, though. You could have picked lots of different numbers, but you would need to be careful because you got to make sure that you're not getting a negative underneath the square root. But you can see really quickly if you look at that 0 is going to be a good choice there. So if I do that, I have 1 minus 0 squared. What's 0 squared?
0.
Okay, what's 1 minus 0? 1. What's the square root of 1? 1. So I'm left with y equals plus or minus 1. So what I have is I have the point 0, 1, and also the point 0, negative 1. Does everybody see that?
Yes.
What can I conclude from that? Is this a function or no?
Yes. Yes.
No.
No, why not?
0,
What's the
0.
zeros?
Yeah, I have a repeated x coordinate, right? So that was a lot of work to kind of do that. I want to point something out that would have made life a little bit easier early on. Typically, if you get the y coordinate or the y value by itself and you end up with a plus or minus, it's a fair bet that that's not going to be a function. So the plus or minus, if you're doing one of these rearrangings to get the y by itself, almost always is going to cause a problem. So just as a, there you go. Okay. Does that feel okay there? Now, these are usually the hardest ones, the ones that are the equation, right? What makes life easier on these is the longer you go, the more of these like recognizable forms you kind of build up as a inside of your math toolbox. And more often you're going to look at these and go, oh, it's something of this form. I know what the graph is going to look like, and immediately just look at the form of the equation and go, oh, that's going to be a line function. Oh, that's going to be a circle, not a function. Oh, that's going to look like do. Maybe that is or isn't. But it starts off hard because, for example, we had this equation for a circle that maybe we would have seen before, maybe not. If you did see it before, it's done immediately, right? You don't have to do anything. If you haven't seen that before, you don't recognize it as a circle, there's a lot more to do to kind of investigate what's going on before you can go, oh, I get it. Like anything that kind of looks like this is going to give me a problem. But you're just not there yet, right? We need to build that up. And that's one of the things that we'll do over the course of the semester when we spend most of the time, first and second semester, studying these different types of functions. So we build up these forms where you look at something and go, oh, that's a exponential equation. I know the graph generally looks like this or whatever. And you're like, you'd already know a bunch of information about it because you can just look at the equation and already have, you already know a lot, which is nice, but we're not there yet, right? Because we're just really new into an algebra course. Because Algebra 1, you do a lot of good stuff, but you don't go very far into algebra. All right. So there's like 8 minutes left. It's probably not a good idea to start domain and range right now because I'd like to be able to do more than just these examples or be able to do all of these examples because some of them get kind of tricky and we probably have to do examples off of the examples and it's not something I can do in 7 or 8 minutes, so let's not start. I want to point out to you that I put the first homework assignment is both on PowerSchool and on the content library here on OneNote. The first page of this is just some notes and just a recap of some of these things that we've done in the notes. The second page is where the problems are. Notice the directions ask you to also write the domain and range. That part you cannot do yet. So if you wanted to start just doing the function or not and why, you're capable of doing that right now. If you just wanted to wait till the next class where we talk about domain and range and then worry about doing the whole thing then, that's fine too. Again, remember the homeworks aren't due till Sunday at midnight. So it's fine. I just put it up there in case anybody was ready to get started on things. You can kind of start some stuff, but if you want to just wait till we've covered the whole shebang that you need to do it, that's fine too. Okay? All right. Well, that's it for me.